it's 2 o'clock, and okay. So I have to keep kind of on top of this, if you don't mind. All right. So we're ready to go. Okay. I'll pick up where we left off, and I'll try to keep an eye on this. What's going on? Let's see. We talked about the glial cells, which are really important. But I would like to let me make sure. I didn't start yet, did I? Oh, I did. So apologies for my distraction. Can't help it. Life is like that. So structural units of the nervous system are the nerves themselves. So we take a little look here at the different categories of nerves. They're fairly straightforward. There's nothing magical with this. This is very basic neuroanatomy. Uh, Except we looked at the gross neuroanatomy, but they were all assembled together. This is the isolated nerve. We call it a neuron. Very specialized. They obviously have to last your lifetime. Extraordinarily rare for them to be anything but amitotic. You're basically born with them. And understand these are the two big players in this: oxygen and glucose. You'll see when we get to endocrine and we start talking about diabetes, high glucose it will kill you, but slowly. Low glucose will kill you right now. And the same thing with lack of oxygen. So that's the really interesting part when we start talking about the brain itself. And again, we have to just because they use the term nucleus for clusters of nerves and clusters of cell bodies. Now we call it the cell body is really the nucleus. That's other names. They'll call it the soma. They'll call it the perikaryon. There's a lot of different names that you will see, but they all effectively are the nuclear area of the nerve. And by and large, our studies will, with rare exception, will look at the traditional dendrite receptor cell body, long, relatively long axon, and then the axon terminals with unbelievable amounts of inputs and unbelievably many amounts of outputs. And so this is a confluence of so many different signals as we look more into it. So here's cell body, perikaryon, soma. This is where everything is basically produced. That's why typically we see a certain amount of pigment, because there's chromatophilic substances. The fancy name is nacelle bodies, and everything occurs there. It's made there. When they reuptake the neurotransmitters, it's recycled there. Okay, and so it has a nucleus, it has a nucleolus, it has some pigments, and the plasma membrane in and around that area is generally, and the dendrite is generally in close proximity. Not always, as you'll see when we look at bipolar nerves, unipolar nerves, maybe a little bit different. Okay. And so again, here's the nuclei v ganglia. They're clusters of cell bodies. It's just whether they're in the CNS, the central nervous system, or the peripheral nervous system. And the extensions, and again, we have different terminology. We call them tracts. We talked about that in anatomy. Okay, bundles of nerve, and we call them nerves, even though they're just bundles and bundles and bundles of axons. We think of them as a nerve, but indeed there's so many different branches. Good. I have to just keep answering these. Hey. Help me. So two types of processes, dendrites and the axon, and it's a classic view. This would be, think of this nerve being in the central or peripheral nervous. This nerve, the cell body, would be in the central nervous system rather, and this would be the long segment that protrudes, be the cranial nerve or from a spinal nerve. And we're looking at an individual axon. You can see the Schwann cells are there. And so remember that now, by definition, we call these now sheath gaps. Gaps in the, and they're there both in the central and peripheral nervous system. Remember the original term that I have so much fun saying. So for everybody who hasn't been here with me before, I love this. And a lot of us still refer to them. We call them nodes of Ranvier. One of the few things I can say in French. kind of rolls off your tongue. Ranvier. Or Ranvier. Pittsburgh it up or New York it up. Ranvier. New York will be Ranvier. I only knows where to be in Boston, but we won't be able to talk to them because they're in mourning today. Is that the saddest Super Bowl performance ever? Was it? No, for New England.
Yeah.
I told you the only Super Bowl I missed was the first Super Bowl for the Steelers. And I'm flying to Vegas with a buddy of mine for a 4-day vacation. Oh, I had no doubt the Steelers were going to do that. We just suffocate them. Maybe a fluke touchdown. Bye. Yeah, how's boring game? So you can see multiple dendrites, multiple areas on the dendrites, this sort of tree, like tree branches with multiple thorns and projections. And you can have as many inputs as you will have outputs. That's the beauty of looking at the nerve, because there's so many different factors that influence whether a nerve, and like the neuromuscular system, where it's all about every impulse says fire, it's just a question whether it reaches threshold. Here we have multiple excitatory and inhibitory inputs. And indeed, you're going to see many of these nerves, particularly in the brain, in the central nervous system rather, have released multiple neurotransmitters depending on frequency and things like that. So sometimes they may be saying fire, and sometimes they may be saying don't fire. Dendrites, hundreds, if not more, little branches, same organelles as in the cell body. Nothing is exciting about this. Not the cell body itself, but all the other things that are there. The receptive input, and we use the term end plate potentials. Remember, at the neuromuscular junction, the question is, do they reach threshold? Here, the terminology is different. We call them graded potentials. And so, just like end plate potentials, they only travel a short distance. They don't get to that area where they can trigger the first sodium and then potassium voltage gated channels. So highly specialized, they have tiny spines, and you can see there's other inputs. There'll be little modifiers saying, it's like I'm telling this one I'm texting with, don't overreact, don't get too excited. It's almost like modifiers saying, okay, I know this is a problem, but before you go crazy, we can deal with this problem. That's it. So there's a lot. Your nervous system sort of mirrors how we would do problem solving. And some people are obviously better than that, and some people, respond very emotionally, and some people more intellectually. And truthfully, there's a certain combination that kind of makes it work. Sometimes you need to release your feelings in a lot of ways. And these dendritic spines are where a lot of these contact points are. You see them shown very well here. These almost like little bumps on these multiplicity of branches. Here's the cell body. Undoubtedly, this is where the impulse goes. That's called the axonal hillock, and this thicker strand that's going. And you can even see on the axon itself, we can modify the message even as it's being transmitted. You'll see it here. They call that, where this initial segment, they call that the hillock. It's almost like the signal comes here, and when the decision to fire, it starts there, and here there's directionality. Unlike the muscle, where it's stimulated, it goes in all directions. Here, that signal is unidirectional. It's only going toward the axon. Once it fires, it's going to go all the way to the axon. It's going to release neurotransmitter. What effect it has on the next nerve or its target depends on what it releases, and indeed, if it's sufficient to reach some type of critical level, a la threshold. So there's a lot going on here. The axon starts with that. They describe it as a slightly raised area or conical area called the hillock. And again, there's so many variations in nerves, particularly in the brain. There's so many more areas that are, again, subtle modifiers. We're going to really deal with typically communication dendrite from an axon triggering a dendrite, triggering an axon, triggering a dendrite. we're going to basically be using that kind of a thing with the chemicals, the neurotransmitters being released. Basically, an electrical system communicating between nerve to nerve or nerve to target by chemicals. We're going to look at that, but it's not the only ones. So another term for them, just like we use the term fiber for muscle, the axons are called fibers. Okay, a lot of collateral branches. Look at the number there, it's massive. The distal endings are called terminals or terminal boutons, is the way you pronounce that. But if you feel like saying button, it's okay with me. Spell it, bouton. The axon conducts the impulse, the transmitter. Another name for it is the axon lemma, just like the sarcolemma, things like that. And it secretes neurotransmitters into the extracellular space. That contact point is still a synapse. Some kind of junction. It can be nerve to nerve, nerve to a target, nerve to gland, nerve to muscle is certainly an example of it. The interesting thing is, because of the differences in neurotransmitters, they can either excite or inhibit. Something you have to sort of burn into your mind. They're not a lot of them. For instance, I mean, alcohol is probably the one everybody's most familiar with. Alcohol, as you will see, is basically called a disinhibitor. What it does, its signal when you ingest alcohol is inhibitory in nature, but it also inhibits those channels that kind of keep us. We're inhibiting channels that keep us from doing something rash, or getting into a fight, or responding aggressively. We all know somebody when they have a couple of drinks is a different person. It's like, boy, where did that come from? Not looking at anybody in particular in this room. I have never seen all of you and I know none of you would drink to excess. It's okay. Just saying. So then, and again, different nerves, multiple times they're doing it. The axons, basically more neurotransmitter come from the cell bodies, but again, reuptake is a big player here. And you're going to see a lot of the therapeutics that are used involve what are called reuptake inhibitors. The whole idea is if we keep the neurotransmitters in the synapse longer, it will produce an effect. And what's interesting is the longer they're there, they actually have modifying effects on the receptors. That's famously, and you might remember me telling you a little bit last time we met about in neuroanatomy, SSRIs. This is where most of when you hear about people taking medications for anxiety, bipolar, obsessive compulsive disorders, eating disorders, all of which are all within the same framework. They're called, not sequential. Oops. It's tough for me to remember all this stuff. Selective serotonin, which is really the big player these days, reuptake inhibitors. By making this more available in the selectivity, you're going to learn that there's more than one type of receptor. That's why there's so many different medicines. They target different receptors, specifically for serotonin, more than anything else, to accomplish different things, whether we're dealing with major depression, whether we're dealing with schizophrenia, or we're dealing with somebody who has a comparably mild amount of depression, maybe just an anti-anxiety type of level. Just saying. And so as you can see, and I want to get back and make sure I have that. Again, many conversations, cell bodies renew. And the trouble is, axons are peripheral axons here. Again, I talked about that a little bit previously. There are nerve repair mechanisms that are there. The ends can seek each other out. It's happened to many of my surgical patients. They can come back together. The closer you get, if you get to the cell body and you damage that nerve's had it. It will not regenerate. There's just the remarkable thing I would share with you is the amazing plasticity of the human brain. It's continual ability to form new. It's like when someone has a stroke. Stroke is effectively lack of blood supply to an area of the brain, and it causes the cells to die. We call that an infarction. Death due to lack of availability of blood supply. Read that as oxygen. People, say, "Oh my God," they said, "Grandma had a stroke," but she's really. I mean, if you had a stroke, there's going to be brain damage. The question is how it affects them. But we have so many ways that we can reroute the circuits and try to circumvent that areas around it. And for those who didn't have me before, I mean, I have an immense amount of personal experience. My granddaughter, who's 8 years old now, had a pediatric stroke. She had a stroke when she was born. She was missing the vast majority of the left side of her brain. She's classified as having cerebral palsy. That's the end place diagnosis. It is. I mean, I had such a difficult conversation when they sent me the MRI. My son and daughter-in-law wouldn't have been able to read that. That's not their area of expertise. You want to have once a guided missile, he can do that. But you want to read an MRI, not doing that. And I saw the damage, and I recounted the story the other day. I said, I saw that. All I could say is, oh my God, they sent me this. How am I going to tell them just how bad this is? And literally, they were told that in some cases, maybe sometimes the best case scenario, she might be able to sit up. She might be able to talk. It's just, and I reminded them, just as I'm reminding you about the plasticity of the human brain, particularly in the very young. She has been able to accomplish. It's never going to be perfect. There's always going to be physical limitations. She's doing all those things, swimming, running, competing. Would it be Special Olympics? For sure. But it doesn't mean she can't do all those things. So I share that with you emotionally to let you understand that it's just remarkable. I know I sound like this guy who's been around forever, but the older you get, all this stuff comes back to you and you begin to see it. And my job, I think, is to relate to some of you, so you, not to take a test about it, but to understand these things, because in everybody's life, stuff happens. And I'm not using the word stuff, if you know what I mean. Fecal material happens. Poop. Shit happens. I'm sorry. Strike that from the record. It's okay. It's like somebody was watching some Olympic event and they caught the hot mic and he said, "This is boring." I can understand it. He was watching that curling, where they're playing shuffleboard. Did you see? Yeah, I saw the crash. Wow. Oh, goodness. So just as long as she's all right. I heard they had to move her to ICU. But I mean, that may have just been. Oh my God. She didn't have support in her left. It's unbelievable. Look, it's like you call I'm here. I'm going to do it. I'm just as long as she comes all right. I don't understand it, but I understand it in that way. The axon. Molecules and organelles are moved along the axon just the way they are in any cell. Motor proteins, microtubules, different tubular pathways, anterograde. Okay, mitochondria, which are down by the axon terminal, cytoskeletal elements that help make those pathways, enzymes, neurotransmitters. The signal is anterograde, going toward the axonal tip. Retrograde, organelles to be broken down, signaling molecules to be recycled. Unfortunately, these, understand, when we deal with viruses and we deal with toxins, they hijack this mechanism just like they do a lot. Understand, that's a real problem with some of the ones that cause us a lot of trouble. They hijack the sampling of our environment. HIV exploits that by attacking the single most important cell in your immune system that we will learn, called the helper T cell. So it's not an innocent process. As you'll see, polio, rabies, herpes simplex, nearly all of us have been exposed to this. And the difficulty is when, and if you, I do not know how much of an emphasis you had in micro. Once you have a herpes virus, you have it forever. Whether or not it breaks out again, whether or not it troubles you significantly is a different matter entirely. Once you got it, you got it, and it's all and it lays dormant. And so, and when it re-breaks out, we have a name for that. We call it shingles. And again, and without going crazy from a micro sense, talking about oral versus genital herpes, which are effectively the same. It's just where they are. There's some subtle differences because they can both occur. Oral can occur in the genital area, genital can occur in the oral area, et cetera, et cetera. So retrograde transport, and this is some of the things because this is a mechanism, these interesting biological mechanisms, can we use this to our advantage? That's what research does. The myelin sheath, again, what's myelin? It's protein and fat. It's basically a membrane. So membranes are fats and proteins. Myelin is very unique in that regard. And effectively, there are layers of protection. The more layers, the faster the signal, as we see, because we're going to take a look at myelinated currents. And we'll probably get started on that a little bit today. So the thicker the nerve is and the more myelin it has, the faster that signal is. So myelin around segmented sheath surrounds it, and most long, with the definition of white matter is myelinated axons, myelinated nerves. Non-myelinated ones, much more slow in that regard. So the Schwann cells, again, are in the peripheral nervous system. And again, it's, you see, it's when they talk about jelly roll fashion, it's like, it could be anything. It's just rolling up a towel that you would have. Maybe you have a beach towel and you want to roll it up because you just want to carry it. Okay. That you're going to incorporate the nucleus close to the nerve, and then the sheaths are just layers and layers and layers of membrane that go around it. So it can be relatively thick. So the outer collar of perinuclear cytoplasm, and in the old days we used to call it neurolemmas. Okay, again, the lemma was code for being membrane, and the bulge was the nucleus that was in there of that particular Schwann cell. Okay, no channels or carriers there. It's just whatever analogy works for you. So whether or not it's the insulation on a wire, perfectly good indication. So it's protective in nature, and it just so happens you will see the signal rather than carried along an exposed wire, has this magical ability to jump from node to node or from sheath gap to sheath gap. We call it a fancy name for that. We call it saltatory conduction, and we're going to look at that in an animation or two. Saltatory means jumping or leaping fashion. So it's rather than it's you'll see. It's okay. I can't help myself using these analogies. I think they're clever. It sort of looks like the original. Maybe I told you. It looks a little bit like the original Super Mario Brothers game, way back when, in the start of those games, in Nintendo games, when he powered up and he went. Super Mario Brothers. You know, with that. It started in the old arcades as Donkey Kong. Up there, and there were gorillas throwing stuff at you, and you're trying to get the princess. To show you how I could operate on people, my kids. I was at level 1 in the first thing, and my oldest had already solved it. And he was like 6 or 7. It's not fair. Don't have children. So here you are, jelly rolling it around. You can see where the nucleus is. I mean, and in this instance, it's farther away, but it keeps wrapping and wrapping and wrapping around. That's why it has that bulge that's there. You can see how thick the myelination is, the myelin sheath, as we call it. Here's the axon. So the axon has lots and lots of tubular structures. This is an individual axon. You can see the magnification, 24,000 times. And you see proportionally how much myelin is there. So the sheath gaps are there. Non-myelinated fibers are much thinner. They're not wrapped. But one cell may even surround. As you can see, they may be surrounded by Schwann cells, but they don't It's not quite the same way. And I mean, you always see them. If you look surgically, you can see them because myelinated fibers are white and glistening when you expose them surgically. And you can see where the end is starting to terminate, the myelin disappears. And it becomes, rather, they almost come like little tiny filaments, but still, if they're large enough, visible to the naked eye that are there. Same illustration. So in the central nervous system, oligodendrocytes, remember it's about room, 60 axons at once. The sheath gaps are still there. They don't have that outer collar. And again, unmyelinated. But again, those areas still are covered by astrocytes. Adjacent neuroglia is what they're talking about. So again, white matter, we talk about white matter in the brain and spinal cord, the tracks. Gray matter is everything else. So gray matter isn't just cell bodies. It's a lot of synapses. It's a lot of dendrites. It's a lot of stuff. But comparatively, you remember from dissecting the brain, those who were there for we did the brain dissection for the sheep, which is most of you, there's a whole lot more white matter than gray matter. It's just showing you the illustration. Cell types of cells. Pardon me. Hey. Hold on. Hold on. So with this, what we were showing you, and I apologize again. I hope you understand. Multipolar, 3 or more processes, 1 axon. Okay, typically the one we see, the one they show the diagram of, by far and away the most common central nervous system. Bipolar, I hope we get a chance to look at today. If not, we'll certainly get into it in the lab because that's about special senses. Bipolar is like a connector nerve that helps in changing the signal. And so what's interesting is it's like when you see something, your light triggers photopigments that change shape. That induces a signal. Now you have that signal. How do we translate that into an image and have our brain understand it? So it's got to take that signal and modify it. That's what the bipolar cell does, and send it to the appropriate area of your occipital lobe for you to interpret. So other than that, so that again, you see that special senses. It's like an in between that's very unique. And unipolar is most sensory nerves. When I reach out, like in the morning, I'm reaching out. Where's the light on the nightstand? It's like you can't see anything, but you feel it with your fingers. That's typical. A typical sensory nerve are almost always unipolar, and you're going to see that they're unique because it's got these 2 long processes that are there, and you're going to see the offset of the cell body. So take a look with them. It's easier for me to show it to you. Here's the typical multipolar. Here is the bipolar. Again, limited. So it will receive a signal from that photopigment. It'll modify it in such a way, and it'll transmit it, and it'll be picked up by another cell that will have basically send it to the appropriate part of the brain, either by a series of other circuits or by itself. Here is the so-called unipolar. You see the cell body. So let's say I felt that with my fingertips here. The cell body is inevitably, we almost always see in the peripheral nervous system. Those are the clusters of those cell bodies make up what are called dorsal root ganglia. When we talked about herpes, that's where herpes viruses hang out. They're in sensory nerve roots. That's the dorsal root ganglia go back and look at the anatomy that we covered when we started looking at particularly the spinal column. You'll see that dorsal root ganglia. That's why a herpes virus, depending on where, it can almost come out anywhere. Like you can, it's just remarkable. Particularly, chicken pox is the reason why we see shingles more than anything else. That's a herpes virus as well, and you get it all over your body, so it can harbor anywhere. So I've seen shingles in the hairline, in the eye, on the face. Dr. Buxton, long before you got, I'm guessing at least 10 years ago, had to miss about 3 weeks. He had a facial outbreak of shingles. Oh, it was a mess. I mean, we didn't see him for about 3 weeks. That was before we were doing all the remote teaching and stuff like that. But he's pretty clever with the computer, so. And just another view of these things. And they show you where they are, and that's good. So effectively, we have sensory, incoming, afferent. Almost all are unipolar. The cell bodies are located in the ganglia, as I'm telling you about. Motor, impulses to the effectors, typically multipolar. Most of the cell bodies are in the central nervous system. Well, when we look at the autonomic nervous system, which is our next lecture unit, we'll talk about this. When I finish this chapter, so I want to get through with this, and we're almost through with that. We'll get it done this week. That concludes the stuff for the exam. I will work on getting you the review recording. I'm thinking the 23rd, because I figured Fridays are bad for our athletic friends that are here. You're probably gone that Friday, the 27th. You must be. But you still have it on Monday. I don't know if you guys have any other fun tests that you're not complaining to me, which is very unusual. It's like it's like you're resolved. It's like you're going to the gallows. I always knew you were just kind of hanging around. Yeah. So that's half a pun. You just ignore me. And interneurons. It's all about these. Everything is processing. Everything is interpretation. When we respond to it, it's like me gauging your reaction to one of my poor jokes. I'm sitting there going, I look at face. Am I getting through to you? I'm looking at facial expressions. I'm looking at attentiveness. Today, I'm not getting. It's okay. None of my other classes. It's all the bad Super Bowl. Everybody would be much more upbeat about it. You're all. It's okay. It's okay. I like all of you most of the time. So we'll get to all that. Thank goodness we're finished with that. What an ordeal. So I mean, that's the whole idea. It's our interpretation. You should be sitting here going, which of this stuff is important, which is not. Because honestly, if you're sitting there, well, I'll wait for the review recording to look at it. I think that's wrong. I had occasion to say this the other day too, with other folks over the course of the weekend. You have an opportunity, not me, because I'm not that smart, but you have an opportunity when you're here at a university with a department that's very receptive to it, to pick our brains. That's what it's about. You get an opportunity. There's so much experience, so much understanding, and you really need to take advantage of that. I'm saying that's true. I didn't do it enough until I figured out that you should do it more. And by that time, you're getting later. That's what you do. That's how you learn things from folks who have, particularly if they're in a field that's even close to something you're interested in doing. I digress. It's okay. They're young. They'll learn. Part B. Because all of you have potential. See? Notice. Not good, right? Potential, membrane potential. We all talked about resting. We're not going to go over it again. Nerves much more rapidly can change it. They're highly excitable. Contrast to what I'm seeing here today in class. I'm not doing it. This is all, I don't ask any questions about it. Voltage, potentials, current, resistance, insulators, conductors, I wouldn't know Ohm's law. Not in the least. But now we get to my area. This is we're getting it back now again to those voltage gated potassium and sodium channels. And again, leakage channels sets the resting membrane potential. That hasn't changed. Gated channels that open and close. And again, chemically gated, mechanically gated, or sensors, touch sensor. I know I'm grabbing something here that's firm. I mean, I've got the phone. I just unloose the phone, which happens all the time here. But you could tell what it was. Like if you're reaching in the old days before we had, now we reach for our cell phone. It's on the nightstand, and then you can see it, right? If I got my cell phone, or am I grabbing the dog? Right? They don't feel the same, even though your eyes are closed. So you have mechanically gated, you have voltage gated, you have chemically gated. And you have ones that are related, photo gated, if you want to think of it that way. Only bond with a specific chemical, being the neurotransmitter. The next PowerPoint sequence is all about that. Voltage gated, open and close. We went over this already. That's why the previous chapter, the neuromuscular chapter, basically is a review. Mechanically gated, responds to physical deformation, pushing, whatever you want to call it, squeezing, pushing. And so we'll see it, whether or not it's a neurotransmitter opens the gate, just like in the muscle for sodium in and potassium out. We saw those. Voltage gated channels now, whether they're closed or open. And then we're going to take a good look at that little swinging guy, because now that becomes important, that inactivation gate, because that ensures more than anything else directionality. It's always going to go in a direction toward the axon, because that's how they're arranged anatomically. And so the signal can't go backwards, it has to go forwards. And once it opens the next channel, then it will allow that other one to reset for the next impulse and the next. And they go through very, very rapidly, to say fast. Okay. Once they're open, we know, and then nothing where the fastest responses you're going to see classifications of neurotransmitters is ones that move ions in and out. The sodium and potassium is moving out, a la the neuromuscular junction. They're fast. The ones that utilize those G protein receptors and that internal things, and then the cascading with the second messengers, they're not by any means slow, but they're slower. That's important. Not doing it, but we can do this. Same deal. Resting membrane potential 70, varies depending, polarized, not going over it. The different compositions, did this already, intracellular v extracellular fluid, and differences in permeability is important. And that related, again, permeability in the instance of the resting membrane. There are more potassium leak channels than sodium leak channels. Permeability and the ability to move across the membrane is a current theme, not just in this concept. Wait till we get to respiratory. You have a big concentration gradient in oxygen, relatively small one in carbon dioxide movement when we get to the lung. Yet they move in equal amounts. Why is that? Because carbon dioxide can get through a whole lot easier. It's much more compatible with getting through the membrane. Membrane solubility plays a role as well. These are the little nuances you need to be familiar with for this course. Whether it's significant to you folks moving forward in your lives, I don't know. But it's the old story. This is part of my task, is to educate you vis-a-vis this. So and we knew this. More sodium on the outside, balanced by chloride. More potassium on the inside, balanced by the negative charge of proteins. Potassium is the big player. Oh, thank gosh we have one of these. So turn it up. I can stop talking.
Contains about 100 billion nerve cells called neurons. A neuron, like all cells, has negatively and positively charged ions in the fluids located both inside and outside of the cell. However, the ionic composition of these two fluids is markedly different. The inner surface of the membrane is negatively charged, while the outer surface is positively charged. This unequal distribution of charge creates a voltage across the plasma membrane, known as the membrane potential. In a resting, unstimulated neuron, this membrane potential is known specifically as the resting membrane potential. The value of the resting membrane potential depends on two factors. The first is the presence of concentration gradients across the plasma membrane, especially those gradients for sodium and potassium ions. The second is the permeability of the plasma membrane to sodium and potassium. In the resting state, this permeability depends on the number of non-gated leak channels present in the membrane for these ions. The magnitude of the resting membrane potential, inside relative to outside, is measured in millivolts using a voltmeter and two electrodes. We'll now place both electrodes in the extracellular fluid. Note that the voltmeter records 0 voltage. This is because the unequal distribution of charge exists only across the plasma membrane. The intra and extracellular fluids are otherwise electrically neutral. However, when we insert one of the electrodes into the intracellular fluid, a voltage is recorded. The value of the resting membrane potential varies, but on average it is minus 70 millivolts.
Okay, we saw most of that before. So again, the resting membrane potential we're familiar with. Sodium potassium concentrations, differences in permeability, just like I talked about. Okay. And that was the pumps. Once again, we already talked about those. So slightly permeable to sodium through leakage channel, and then 25 times, that's a lot, more permeable to potassium, etc. And chloride's interesting. We're really going to get into chloride channels. Chloride channels are very, very significant. For instance, I talked about alcohol. That involves chloride channels. So differences in plasma membrane permeability. More potassium diffuses out than sodium diffuses in. We knew about that. Balanced out by the sodium-potassium pump. We knew about that. Don't have to go there. Don't have to go there with almost any of this stuff that you're seeing here. It's just not required because we already did it. That's the beauty of having gone through this fairly, I thought, comprehensively. So, and what happens to changes when the concentrations of ions across the membrane changes, different kinds of permeability. And again, only two types of potentials. Graded, you're going to see, graded means they are not enough to reach threshold, and an action potential if it does. Really. And so these are the way the information is basically sent. Integrated means incorporated, all the things. So hopefully you're being able to tell, when I go over something very rapidly, either we've done it before, like some of this, or it isn't, I'm not going to ask you a test question about it, or something I don't know enough to teach you about. Little things that you pick up, but you're in the latter years of college. You should have all this stuff down already. You should let me help them do freshman seminar with Dr. Hannah and Dr. Dress. They all look at me like I'm a crazy person. Why are you having this old guy talk to us? What the does he know? So, and again, we use different terms. Depolarization, more likely to fire. Hyperpolarization, less likely to fire. So depolarization, less negative or more positive. Probability increases of an impulse. Hyperpolarization, taking it farther away. Again, the difference between this and a neuromuscular junction, every signal of a neuromuscular junction is more likely to fire. Hence the different terminology. We don't have things that make it less likely to fire. Here we do. That's the beauty of the nervous system. And so, closer to threshold, farther away from threshold. This is rest. And threshold, they're using 50. Here's the minus 55, typical number that we see used. Graded ones are short-lived, localized. They don't get to those embedded start of the voltage-gated first sodium and then potassium channels. just like on the muscle fiber, but a little different. Okay. And so it depends. So named according to the receptor, graded potentials are like that. Postsynaptic, I don't really go crazy about using that, but you'll hear it in some of the discussions. I'll talk about what the receptors are like and what the postsynaptic potential, and really what they're showing as we conclude for today, without new stuff, is if it's just a graded potential, it'll change in one area, but it will degrade quickly over the space of the nerve where it's triggered. And so it will induce changes, as you can see, in localized areas here and here, but it doesn't last, it dissipates quickly. So they're only short distance signals. And so the area is somewhat limited. And you're going to see the difference when we start talking about action potentials. We will resume with that on Wednesday. Okay. So give me some time to set up, and hopefully this other situation resolves. And so I hope we'll get started by 10 after 3. I got to go back, get my office computer, hook that up with the high def lead in the ecology lab, and then hook the other stuff up. Okay? We're good? Thank you. The environmental science lab. Gee, didn't you see all the comfortable chairs? Did you guys get soup yet today? Did you get cake yet today? Here's cake, my wife's birthday cake that she really, sometimes it's hard for her to choose stuff. And did you have some of the soup? Did anybody have the potato soup yet?
I had all 4 soups.
That's what I did. The only way you can test. Stop.